Would you grab the door for me? Thank you.
I haven't had a singular 10 or 9.
All right, I have rewatched a few of the recordings that I made over the semester, and I found that for the first 10 or 15 seconds of each recording, for some reason it jumps and skips, and like the camera can't quite keep up. You guys, some of you who may have watched the YouTube videos, maybe you've seen that. So hopefully by allowing the recording to go for about 20 seconds before I started talking, we're not missing any vital information now. Okay. Welcome back to Physical Geology 1403. We have lecture 6 today. This is the last lecture in week 3. Had to count there for a second. Week 3 out of 8. We're getting through it. All right. Let's see. Any announcements? I think I pretty much filled out all the announcements that I had the last time we met on Tuesday. Just a reminder that your first exam will open 1 week from today.
Yay.
We will have an exam review 1 week from today.
Also, yay.
So come prepared with your questions. And for my online students, please make sure that you send me your questions no later than next Wednesday night. If you wait to send them to me on Thursday, I do not guarantee, cannot guarantee, that I will see them before I begin the exam review. So please send them to me no later than Wednesday night so I can look at them and answer them for the exam review in front of everyone. How are we doing? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 23. Huh, we're all here except Ashton and Jose, I guess. But I haven't seen Jose in a few days, like a few lectures. Do you know where he's at? No, sorry, not Jose. Sorry, Joe. Sorry. Joe usually sits there, and I saw you there, and I said, Jose. You don't know where he's at? All right. All right, fair enough. Hopefully he watches these and knows that we're thinking about him. All righty. Questions for me? Anything at all? I know that the subject of politics is not something that I linger on very long in these lectures, but the world is changing fast. Our country is changing fast. Day by day, things are different. Some people are pleased, some people are not. I had a very personal reason to be rather displeased yesterday when I received a notice that the partnership with Lawrence Livermore National Laboratory that I've spent 6 months putting together has been canceled because of President Trump's freeze on all government-funded research until they can determine whether or not it is worth pursuing. So it was supposed to start next month. Basically, it was going to be a series of public presentations that I give out in the Permian Basin, specifically for scientifically underrepresented communities in our area, mostly Hispanic communities, where I was going to be making sure that those people get the information they need to know about certain geological subject matters, namely the earthquakes. Y'all have felt the earthquakes we've had around here, right? It's a matter of concern. A lot of people have questions. I get bombarded by questions for weeks after we have an earthquake. And so the whole point of this was to get information, educational materials, and public presentations out to the parts of the community that don't have access to resources typically to answer their questions. It has been put on hold, probably going to get full-on canceled. But that made me kind of sad yesterday because we put a lot of work into putting that together. Yeah, it's okay. I'll get over it. Good? No questions? No comments? No songs or dances? Yes?
Do you hear about the collision, I think, in Boulder, Washington?
The collision of what?
Black Hawk and airplane, like a commercial.
I did not hear about that. When was this?
I think it was either yesterday or this.
Yeah, that would probably explain why I haven't seen it. I typically will check the news. Like, I'll go through my email. I get geological news and stuff in the mornings, but I don't like jump on the news websites or anything like that until after I'm done with class. I don't usually do. That's not part of my morning routine, but I'll do it in the afternoons usually, after when the day has had more time to move on. Okay, so that's unfortunate. A commercial airplane and a Black Hawk collided, you said?
Yeah.
That is very weird. Black Hawks
Yeah.
can't really get enough altitude typically to be anywhere near where a commercial airplane.
It was landing in there.
Why was a Black Hawk landing at a commercial airport?
The plane was landing there.
Yeah, it would make
The Black Hawk was taking off.
Again, Black Hawks at civilian airports is not typical. So I don't know what was going on with that, but that is very unfortunate. Sorry to hear about that. And this is in Washington State?
I'm pretty sure.
At Reagan Airport.
Reagan. Oh, so it was in Washington, D.C.
Yeah.
Oh, okay. Sorry, in my head, I'm thinking for a Black Hawk, a military Black Hawk, such a valuable piece of hardware to be at a civilian airport and leaving, it had either just picked up or dropped off someone very important. If it's a DC we're talking about. Okay. All right. Did not know about that. Thank you for informing me. Anything else? Anything we want to talk about? No? All right, well then let's begin. You've already learned about igneous rocks, right? Igneous rocks are formed from magma, right? Magma crystallizes, makes your igneous rock. We learned about the process of weathering and erosion, the breakdown and transport of rock, including igneous rock, right? This is where we get sediment. But our next step in the rock cycle is what happens next to that sediment. It becomes a new type of rock, sedimentary rock. I know, who would have seen that coming, right? Sediment becomes sedimentary rock. Now, about 90% of the total mass of our crust is igneous and metamorphic rock. Worry not, we will talk about metamorphic rock next time we meet. That's 90% of the total volume of the crust, meaning that the other 10% must be sedimentary rock. However, that 10% of the volume of the crust that is sedimentary rock represents 70%, about 70% of all rock exposed at the surface. So most of that igneous and metamorphic stuff is buried underneath a top layer of sedimentary rock, which makes sense because where is sediment formed? On the surface, right? Did you say on the ground? I mean, yeah, I understand what you're saying. It's just the words, right? On the surface, okay? Since sediment is formed on the surface, sedimentary rock is formed near the surface. Therefore, we have a very broadly distributed outer layer of sedimentary rock on the surface. Now, sedimentary rock is cool. We use it for a lot of stuff. Even though it is not the most common crustal rock, it's the one that we most commonly interact with. Why? It's a very simple answer. And we live on the surface. Exactly. We live on the surface. It's the most common rock on the surface. Boom, bada boom. And most influential in our lives. Typically, as you go throughout your day-to-day life, you are more likely going to see more sedimentary rock than you are the other two, especially where we live here, right? Igneous rock, metamorphic rock, those typically are exposed at the surface whenever you have mountains or things like that, or valleys or any of those. We don't have a whole lot of topography here, right? But what we do have is a lot of flat depositional landscape, which is mostly sedimentary rock. Okay, now sedimentary rock is great. I love studying sedimentary rock. Most of my experience has been with sedimentary rock, not only because it's the kind that we're most exposed to, but also because it is the kind that preserves stuff in it. We have learned how to identify the chemistry of igneous rock to learn more about its origin and the ways that it changed over time. But sedimentary rock has the ability to preserve other things in it. Evidence of erosional weathering patterns, right? Both of those things. Also, directions of current flow. What things lived there? Fossils, right? We can only find fossils in sedimentary rock. Why can't we find fossils in igneous rock?
Because they'll melt away.
Right. Nothing that came from anything alive would survive being in magma. So we're not going to find any in igneous rock since that comes from magma. Little bit of a precursor of metamorphic rocks. Metamorphic rocks are what you get when you heat and pressurize any previously existing rock to the point where it changes chemically and physically. Why wouldn't fossils survive that? Yeah, they would fall apart. They would also recrystallize like the minerals around them, and there would no longer be a fossil left. So sedimentary rocks are the only kind that can preserve things like fossils. Okay, and I have a few examples that I'll be showing you here later today of some cool fossils. And then also many of the resources that we rely upon can only be found, can nearly exclusively be found in sedimentary rock. Oil, for example, almost entirely, almost always is found in sedimentary rock. It usually comes from a type of rock called shale. We'll talk about that today. We often find it, at least the conventional plays of oil, that we can stick our well straws down into and will come up, and it's really easy to find, right? We'll find that in sandstones, sedimentary rock. There are a few exceptions to what I just said. I said nearly exclusively, right? 99% of the time you will find oil in sedimentary rock. There are a few rare circumstances where we have found it in other places. In Vietnam, there is an oil play where they pull oil out of granite, not because the granite made oil, but because the oil was formed in sedimentary rock somewhere else and then flowed into all the cracks and spaces in the granite, and now they can drill into the granite to pull it out. It's a very interesting, unique circumstance. But most of the time, it comes out of shales and sandstones, aka sedimentary rocks. So we have the weathering of material. Weathering is what's happening to my material? It's breaking down. Thank you. Mass wasting and erosion. Transportation. Deposition and diagenesis. These are new words that we're going to talk about today. What does deposition mean?
Depositing sediment.
Mm-hmm.
Process of depositing sediment.
The process of depositing sediment. What does that mean? What does depositing mean?
Dropping something off and leaving it in one place.
Dropping something off and leaving it in a place? Yes. Something stops moving, right? When an object stops moving, it is deposited there by whatever was moving it, right? You pulled into the parking lot this morning in some vehicle, a bus or a car, whatever that may be. As soon as your vehicle stopped moving, you got out and here you were deposited at this location, right? So our sediment is deposited. Diagenesis. Diagenesis has a whole slide devoted to discussing it here in a little bit. But for now, I'll just say diagenesis is any change that occurs to that sediment after it is deposited, but before it reaches certain heat and pressure thresholds like metamorphism. Okay? So that encompasses a lot of stuff, including the process of becoming a sedimentary rock. That happens in diagenesis. We'll get there here in a little bit. For now, let's talk about the different types of sedimentary rock that you can find. We classify sedimentary rock into clastic and non-clastic sedimentary rocks. These are things that are very relevant for your lab. You are, in fact, getting lab 3 today, by the way, sedimentary rocks. So clastic sedimentary rocks are those which are formed out of the broken bits and pieces, the fragments of mechanically weathered rock. Someone remind me what mechanical weathering is.
Wind. Water.
Doing what? You're telling me things that can weather, but you're not telling me what mechanical weathering is. Weathering in general is a natural breakdown, but remember we have mechanical and we have chemical weathering. What's the difference between the two?
Mechanical is physical changes.
Mechanical is physical changes, okay. Physical breaking. Like if I took a hammer and I smashed a rock, think of that, right? Going from large pieces to small pieces.
It'll break down physically, but it doesn't change like chemically.
Right. We're not talking about chemical changes, just the physical changes. Thank you. That's a good observation. Great. Which means that chemical weathering is, yeah, we're getting some form of chemical alteration, like through the addition of some acid that's altering it, breaking it down, removing parts of its bonds. Great. Thank you. So, clastic sedimentary rocks are those which are made from the broken bits and pieces of mechanically weathered rock. Non-clastic sedimentary rocks are those made from chemically weathered rocks. So in chemical weathering, something gets dissolved. It's dissolved. There are parts of it in the water. That water carries it somewhere. Those parts start to recoalesce, recrystallize, and you make a chemical or non-clastic sedimentary rock. And then there's another subcategory of non-clastic called organic. There's only really one example of that you're going to learn. Anyone want to guess what that is? It has to do with fossils. There are versions of organic rock, non-clastic rocks that have fossils in them. Coal is what I'm looking for. Yeah, coal. Did you know that was a rock?
Yeah.
Coal is a non-clastic sedimentary rock. It is made from plant matter, primarily. Okay. Now, there are other types of non-clastic sedimentary rocks that have other fossils in them, pieces of shells and whatnot. This is where things get a little bit tricky as far as classification is concerned. There are geologists who contend that things like fossil limestone, such as this, which is made out of shells and pieces of skeleton, there are those that contend this should be considered an organic, non-clastic sedimentary rock because it is made from pieces that at one point were parts of living organisms. There are others who contend that because there is nothing organic left in it, it should be considered simply a chemical sedimentary rock and non-clastic. So for the purposes of this class, to make things simple, let's simply refer to them as biogenic, okay? So we're going to put them in the organic category, but not quite the same thing as coal, where coal is directly organic, having those organic compounds of hydrogen, carbon, and oxygen, right? You can't really burn fossil limestone as a fuel, but it does have bits and pieces of previously living things in them. So we're going to call it organic for simplicity's sake, okay? All right, now let's dive a little bit into clastic sedimentary rocks. How do we classify them? How do we tell them apart from each other? What are they made out of? That's a huge factor. The most common ingredients in clastic sedimentary rocks are quartz and clay. Let's talk about quartz first. Why would quartz be a very common ingredient in clastic sedimentary rocks?
Because you can easily find it.
Why is it easily found? Why do you say that?
I don't know. Is it because it's on the surface? I mean,
It's on the surface. What surface? Where surface? Which surface? Whose surface? No.
I don't know.
You know? Anyone want to help him out? Okay, both of you said something very important there. Let's come back to your subject of beaches here in a second. What'd you say? It is found in granite a lot, and granite is found where? Which part of our planet's surface has a lot of granite? Remember, there are two subdivisions of our planet's surface? Yeah? Mountain ranges, which we find on continental crust. Okay, so we have a lot of granite in continental crust. Granite is rich in silica, aka quartz, right? And so it gets broken down. How hard is quartz? Pretty hard, right? Harder than most other common minerals. So it's going to be like the last thing that breaks down. Everything else around it breaks it down, which means that we get a lot of it built up on the outer edges of our continents, which we call Marquez
Sand.
at
Beaches.
beaches. We get a lot of quartz sand on our beaches, built up at the beaches where water often carries this quartz. It gets left there. You do not find, for example, quartz sand in the middle of the ocean. Cough, cough. This is a question on your lab. Why wouldn't we find quartz sand in the ocean? Why would we only find it near continents? Because the continental crust is rich in granite, which has quartz, and quartz is hard, therefore it breaks down slowly, slower than most of the other stuff. And what did Marquez figure out? It goes where?
Beaches.
Beaches. It gets built up on or near continents, but not in the middle of the oceans, because the middle of the oceans does not have all that granite with all that quartz. It has basalt. Basalt doesn't have quartz, right? You see how we did another logic train there? I didn't tell you anything new in any of that. You guys tied that all together yourselves, stopping along at different train stations along the way until you ended up at the destination to answer my question. Why is quartz so common in classic sedimentary rocks? Because of this process. Continental material breaks down, leaving behind quartz for a longer period of time, and so it gets incorporated into sedimentary rocks. Right? All right, now what about clay? Remind me where clay comes from. There was one mineral I talked about that weathers down into clay. There are many that do, but there was one in particular that is very common. Huh? Rainforest soil has a lot of clay in it, but that's not where it comes from. What very, very common mineral on Earth's surface, it makes like 50% of the crust, we think, right? What very common mineral weathers into clay?
Silicate?
Huh?
Silicate?
It is a silicate, but remember, silicates are a classification of minerals, not a mineral itself. Limestone is something we're learning about today, not a mineral. Feldspar, yes! Feldspar, very common on our surface, present in both basalt and in granite. Okay, so out in the oceans and on land, and weathers into clay. 50% of our Earth's crust is made out of a mineral that weathers into clay. So does it make sense that clay would be the next common ingredient in classic sedimentary rocks? Yeah. Yeah, very simple reasons for why these are the two main ingredients, right? Easy to understand reasons once you tie those ideas together. Now you can have larger chunks of these things in there. There can be pieces of feldspar. There can be chunks of quartz in my rocks. They don't all necessarily have to be small in size, and actually size is what we will talk about next. The particle size, or grain size, as you will see it referenced on your lab. What does that tell you? If I have larger grains or smaller grains, by the way, we measure these grains in millimeters typically. Each of you in your test kit, or if you're watching this online in the YouTube videos, you'll see me put each sample next to a grain size chart. There should be grain size charts in many of your test kits. Some of them have walked off over the years, so I'm missing some, but there should be a number of them out there. We may need to share them. But we measure it in millimeters, or you could simply say very fine, fine, medium, and coarse. Okay, so down here in our very fine section, okay, less than 1/256th of a millimeter, it's microscopic, right, is clay. Anything between 1/256th of a millimeter and 1/16th of a millimeter is called silt. And if you can see that with your naked eye, I am very jealous of your vision. I cannot. Anything between 1/16th and 2 millimeters is sand. You could think of that as medium-sized. Okay. Anything above 2 millimeters, we just generally call gravel, but it can go from granule size to pebble size to cobble size to boulder size, right? Look at that boulder. That's a nice boulder. What movie is it from? Shrek. Thank you. Good. Okay. All right. So those are grain sizes. What does, there's a lot of birds that just flew past this. What does the grain size present in our classic sedimentary rock tell us about the grains? We look at these sedimentary rocks and read a story from them. Each property tells us something about its story. What would grain size tell us about the story of that sediment?
Maybe the environment and how durable it is.
What about the how durable it is? Okay, sure.
How much the environment matters.
Weathering. How much it broke down, which could also tell us something about how far from its source it is, right? If I have very, very, very tiny pieces, it probably came pretty far. If I have large chunks, it's probably pretty close to its source, right? Grain size. Now sorting. Oh, well, sorting is how close in size all those grains are. So I can have a sandstone that has fine to medium grains in it. Okay? But I need to determine what the sorting is. So if it has kind of a range, I would say fine to medium, let's call that moderately sorted, because I have multiple different sizes in there. If it's all 2 millimeter sandstone, I would call that well sorted. It's all the same. If I have fine to gravel sized pieces in my rock, I would call that poorly sorted. What does the sorting tell us about the history of this sediment? Any ideas? That looks delicious. What are you drinking? Ocean breeze? What does it have in it? That sounds excellent. The only problem I have with that is the Red Bull. Red Bull would kill me. I am caffeine hypersensitive. One drink of Coke and my heart starts racing out of control and I see spots. Yeah, I'm pretty sure a Red Bull would kill me. To a what? A fizz? What's a fizz? Oh, just a carbonated. Okay. I might try that. That looks really good. Okay. Let's go back to the subject at hand. Sorting. What does that tell us about the history of the sediment?
Pressure.
Not pressure, but I like where your head is going. Something else, some other force, some other factor here.
Type of weathering?
Not the type of weathering. Let's further the plot a little bit, okay? If I have a bottle or a container and I fill it with water and I dump a bunch of beads of different sizes. Let's say I've got 2-inch beads and 1-inch beads and 1 centimeter beads. And then I close that and I shake it. How many of those beads are moving? All of them. But if I start shaking it slightly less, if I put less energy into it, which beads are going to settle to the bottom first? Why the big ones? They have more mass and therefore require more what? Energy to keep moving. So as my energy is dropping in my system, the smaller ones are going to keep moving. The medium ones are going to keep moving. The bigger ones are going to settle out first. And then I drop the energy a little bit more, right? The medium ones settle out. And then as finally I stop moving it entirely, the small ones will settle out at the bottom. And so I'll see this sort of layering effect with larger, medium, and smaller. Now imagine that this is a river. And over the course of my river, I go from high energy near the source of the river with large particles, medium particles, and small particles all in that water. And as it goes on its way over hundreds of miles towards the ocean, I'm going to be losing energy over time. And so near the source, I'm going to have my larger sediments deposited. I'll get gravels. And then about halfway along the way, I'll start depositing my medium sediments. And then finally, towards the end of the river's journey, I'll deposit all the smaller sediments because it'll have the least amount of energy, right? This is the big factor for determining sorting, or what sorting means. If I have a very well-sorted rock, that means that I could be looking at an energy regime according to that grain size. If I have a well-sorted, large-grained rock, I could be looking at a high energy, right? A high energy water source, like a river. Medium, moderate energy source. Fine-grained rock, very low energy source. Because it takes very little energy to suspend those, which means that if those fine sediments finally settle to the bottom, there must be little to no energy in that system. Okay, you following the logic here? Good. So if I have a whole mix of them, let's say, fine, medium, and large, all in the same rock, very poorly sorted rock, what does that mean? Instead of energy being lost slowly, energy must have been lost like that. If I have that bottle or that container and I'm shaking it very vigorously and all of the larger and smaller and medium particles are all suspended, and then I just all of a sudden stop, is it going to go large, medium, small? Or are my small ones going to say, all right, I'm just going to wait up here at the top while the large ones go, and then, okay, yep, all the mediums, okay, now I can fall. No, they all fall at once. And so they're all intermixed with each other. And so when I see a very poorly sorted rock, I know that energy was lost quickly in that system. See how I'm kind of piecing together clues about the history of that area based upon the characteristics of my rock? I know that there was flowing water here. I know that energy was lost quickly. That may have been a landslide. That may have been some sort of debris flow. Okay, a mudslide perhaps. Okay, where energy was gained, picked up speed, and lost very quickly. Okay, I'm making interpretations based upon physics, basically. Okay, so that's sorting. And then there is shape. We label grains on their shape on a kind of a scale from angular to rounded. So you've got angular and subangular, and then there's subrounded, and then there's rounded on the other end of the spectrum there. Why would the angularity or the roundness of my grain tell me anything about the history of that sediment? What did we learn about things as they get rounder? Why do things get rounder? Weathering does what?
It grinds down its surface area.
Corners have more surface area, right? We learned about this with river stones. Corners have more surface area, and therefore they get weathered down the fastest, giving us a rounder particle. Whether that's a river stone or a tiny, tiny little piece of sand, it's still true. So the rounder my grains are, the more what they got? Weathering. Bingo. So that tells me a little bit about the life cycle, how long that sediment was weathered before it became part of that rock. This is fun. This is like, you're like Sherlock Holmes of the natural world. You're taking all these clues and putting them together to figure out what happened to the sediment before it became a rock. That's completely independent of the other things you could find in it, like structures or fossils, right? Which we'll get to. Anyone want to hold the snake? Sorry, I saw his hand here first. We'll go for that next. Huh? Press the button?
Step out.
Oh, step out? Yeah, sorry. I thought you were saying, mind if I press the button? I'm like, I need to know what the button does first. Okay. Any questions about classic sedimentary rocks before I hand a few around? No? Okay. Well, let's talk about shale first. Shale, classic sedimentary rock, clay to silt-sized particles, often found in very thin layers. When I find a shale, because it has such small particles and I find it in very thin layers, I can make some pretty sure interpretations about the environment it was formed in. For example, the fact that it has such small grains tells me that it must have been very low energy. The fact that I find it in a rock that has very thin layers of these clays and silts means that it must settle out of this very calm water slowly, perhaps seasonally. Maybe I get a very thin layer that's deposited during the winter, and then very few in the summer, and then another very thin layer deposited in the winter, or the opposite, a lot deposited in the summer, and then none in the winter, and then some in the summer, right? Thin layers, very small particles. Shale is often the source rock for a lot of oil that we find. Have you ever heard the term conventional play and unconventional play? Any of you that are in any way associated with the oil field? No? How many of your dads work in the oil field? Okay, there's a few. All of you have seen the pump jacks that we have in town, right? If you've lived in Odessa for a day and you haven't seen a pump jack, you obviously haven't gone outside, right? They're all over the place. What are they doing? Those pump jacks are wells that are drilled in the ground and are pumping up oil from some source. Now, a lot of the sources that we would target all the time in previous, I was about to say decades, but now I can say centuries, we've been doing this for a while, right? Are what we would call a conventional play. Very easy to understand. There's a body of some rock that has a lot of space in it to hold oil. You poke your straw in it, the oil comes out, boom, bada boom, crude. There it is. That's more of a conventional play. An unconventional play, as the name implies, is something that's not quite as straightforward. It requires a little bit more work. Okay? So instead of simply having a rock like a sandstone, which I'll talk about here in a minute, that is a conventional play. Instead, you would need to target, say, a shale. Shale has a lot of oil in it. It's where the oil forms most of the time before it migrates out into something like a sandstone. And so you target something like a shale, in particular a black shale. Shales take color based upon what is in them. Very similar to what we learned about quartz and other minerals and stuff, right? Black shales are rich in organics, usually things like oil. Green shales, those can be rich in chloride. Red shales have a lot of iron in them, so on and so forth. Okay. We'll find these in lakes, floodplains, lagoons, deep oceans, most commonly in deep oceans because there's a lot of that, right? Pass that around. That's a shale, actually. I'll bring this back. Let me put it in front of the camera for a second. Okay. Here is a shale. You can see that color. You can see the very thin layers in this cross-section view there. Okay. Now I'll pass it around. Thank you. Sandstone. Now, what size particles do you suppose sandstone is made out of? Sand. You were paying attention, right? Okay, sand, which corresponds pretty much to medium. Okay, 1/16 to 2 millimeters in size. We'll call that medium. Now, the principal ingredient in most sandstones is quartz. Quartz takes a long time to weather down. Let's hesitate on that thought for a moment. Let's do another logic train here. Why does quartz take much longer to weather down at the surface? It is harder than a lot of the minerals around it, but it's just as hard as olivine. Olivine also is a 7 on Mohs hardness scale, but olivine breaks down very easily, right?
Its chemical bonds are stronger.
Its chemical bonds are stronger. But isn't that dependent on a few things? Aren't the strength of chemical bonds dependent on one thing in particular?
Temperature.
Temperature being an aspect of the environment, right? Yeah. Let's talk about temperature for a second. At what temperature do olivines form? Do y'all remember? It was the first thing that formed in our magma chamber experiment that we did with the M&Ms. You remember what that first temperature was? 1200 degrees Celsius. Do you remember what temperature quartz formed at? 400 degrees Celsius. Now, which one of those is closer to conditions here on the surface? 400. Now, that's still pretty far away, right? But a quartz that forms at 400 degrees Celsius and at pressures much closer to Earth's surface than olivine, quartz, therefore, is more stable at the surface than something like olivine would be. Okay? Therefore, while olivine breaks down very quickly under surface environment conditions, quartz will break down far slower because it is naturally more stable at these conditions. Does that make sense? Good. Okay, now let's get back to this rock. Sandstone, principal ingredient, quartz. Why? We have a lot of quartz. We get sandstones, you guessed it, at or near continental boundaries. On continents or near them, like in a beach sort of environment. Okay, that's where sandstones come from. Now you can get a sandstone that is almost 100% quartz, like this guy right here. Very pale white. Why? Because this is a lot of clear or milky quartz, tiny little grains of it that have been compacted into this rock. This is a quartz arenite, I would call this. It's not necessarily something you need to know. Just call it quartz sandstone. Okay? This is a quartz sandstone. And yes, it has all the same properties as quartz that you learned from lecture 2 and lab 1. You can scratch glass with this. Just like that solid chunk of quartz right here will. These two things have the same properties, except for the fact that this is one crystal and this is a billion of them that have been weathered down into these rounded little grains. Okay? Both will scratch glass. Both have the same density, both have the same color, same everything, except that this one you can still see the crystal form because it's one crystal, right? Okay. Okay. Let's pass that sucker around. Now, there are a few variations of sandstone. That's a quartz sandstone, but if I have a high quantity of feldspar in my sandstone, feldspar pieces, high quantity meaning 25% or more of the grains in my rock are feldspar, I will call it an arkose. Now, this is still like 75%, or maybe 60%, or maybe 50% quartz, but there is a high enough concentration of feldspar grains in here that I got to call it something a little bit different. It is still a sandstone because sandstone is dictated not by content, but by size. Still a sandstone, but instead it's a variation called arkose because of the quantity of feldspar in it. Okay? And when I have a sandstone that is still mostly those sand-sized particles, quartz, a lot of it in there, but has 15% or more clay particles in it, that's enough to throw off the color. It's enough to throw off how easily you can see the quartz in there. We call that a gray wacky. This is a gray wacky. And that is sandstone. Now let's talk about what we get with larger grains. When I have greater than 2 millimeters in size particles, so you know, it's gravel size, the big sizes, coarse, very coarse sizes, right? Mostly those larger particles, but they are bound together by small whole bunch of larger particles. Now, there are two flavors of conglomerate. When you have nice, well-rounded gravel, larger particles in there. Do you smell anything, Abigail? What does it smell like? It smells like sand. Good, it should. What does sand smell like? I don't know what sand smells like. Okay. It's what? It smells like the ocean? So you're telling me if I do this and I smell that sandstone, I'll basically be at the ocean. Like I close my eyes, like I'm there, right? Interesting. I did not know that sand smelled like the ocean before. Okay, so when I have a conglomerate with rounded grains, I call it a conglomerate. That's literally just his name. But when I have a conglomerate where the grains are instead angular, aka unweathered or very, very lightly weathered before they became incorporated into that rock, it's a type of a conglomerate that I call breccia. 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 Huh? Double C's usually make a ch sound. Yeah. Breccia. Like you breccia.
I thought they made a sound.
That depends on the language.
What language is it?
Where does breccia come from?
Is it Italian?
My bet would be on either Latin or Greek. Most scientific names come from either Latin or Greek. I don't know which one breccia is.
I see the I after the two C's. Yeah.
Yes.
That's
Ch. Yep. Yep. Okay. It's probably Latin. Italian. All those Romance languages are based off of Italian. Spanish, French, Italian, Romanian. All of them are based off of that. Okay. So look at how angular the pieces in this are. And they are bound together. In this case, this is all bound together by calcite, a calcite cement. I'll talk about cement in a little bit. But you can see that these are all very angular chunks, which means that this rock was formed before all of those smaller pieces, these gravel chunks, were able to weather away and get their corners removed, right? So this rock broke and then relatively quickly got turned into a rock, a different rock, a sedimentary rock. Breccia. When they are rounded, it's conglomerate. When the pieces inside are angular and larger than 2 millimeters, it is a breccia. It's Italian? You looked it up? Nice. Love it. I know now. I love learning things so that I can not say I don't know the next time. A scientist isn't afraid to say I don't know, but he sure loves not having to say it. Okay. Now, these obviously form in higher energy environments. Mountain streams, glaciers are very slow moving, but have so much energy in them. Imagine the energy bound up in moving millions of tons of ice. I'll Just trying to hand you a rock. No worries. Okay. Any questions about clastic sedimentary rocks before we move on to non-clastic? No? All right. Non-clastic then. You get non-clastic sedimentary rocks in a couple of different varieties. Inorganic, non-clastic sedimentary rocks form through the natural process of crystallization, usually through two things. You can get evaporation. So in the case of this example up here, have any of you ever been to Yellowstone? Oh, no worries, no worries, no worries. Grand Canyon is also cool. But Yellowstone, no one's ever been to Yellowstone. Okay, you have. Okay, when you go to Yellowstone, there are going to be a few places like this. These are hot springs that come out of the ground and then deposit layers of rock into these step formations. We call this travertine. This is a variety of limestone. What you're looking at here are layers of calcite that have built on top of each other as this hot spring water comes out of the ground. This water has gone through a layer of limestone underground somewhere. It's become saturated in dissolved limestone. It comes out on the surface, and it deposits all of that. As the water slowly evaporates away, it leaves behind what was dissolved in it, just like the salt in the bottom of your glass or the sugar in the bottom of your glass that I used as an example last time, right? When I was talking about chemical weathering. So we get layer upon layer upon layer upon layer upon layer from the process of evaporation. That is one way you can get inorganic, non-clastic sedimentary rocks. You can also get it through crystallization in the oceans. There are several different types of limestone you're going to learn about today. You just learned about travertine. Now you're going to learn about a different one. This one is called micrite, M-I-C-R-I-T-E, micrite. Micrite forms through temperature change in the ocean. Now, remember that we learned that when you dissolve certain minerals in the ocean, you're going to end up with that bicarbonate, right? And loose calciums and things like that. Well, eventually a bunch of that makes its way out to the ocean. So our ocean water is rich in all these dissolved minerals, some of which are utilized by organisms to make shells or skeletons. We'll talk about that in a minute. But a bunch of it still remains just dissolved in the water. Now I'm going to share a little something with you that will help you out as geological Sherlock Holmes is here. Okay. Calcite dissolves easier in cold water. What? Doesn't everything dissolve easier in warm water, right? Don't we dissolve things in warm water? You add your salt to the boiling water for your pasta. You put your sugar in warm tea, not cold tea, right? And yet, calcite will dissolve easier in colder water, which means that it therefore will precipitate easier in warm water. So when you have a warm sea, those loose calciums and bicarbonates will often recombine together and make calcite crystals in the water. And they will fall down to the bottom, collect there, fuse together, and make micrite limestone. This is a collection of microscopic, tiny, tiny little calcite crystals that all fuse together at the bottom of a warm ocean. Okay? Micrite. Made out of calcite. Yes, it will fizz with hydrochloric acid. Feel free to test it while I pass it around the room. Prove me right. Okay? Okay, and then there's our organic sedimentary rocks that are made out of shells and skeletons and plant matter, right? I'll pass a few of those around the room when we get to them in a second. You have a picture of some here. This is I would call this a crinoidal limestone. Why? Because every single shell, every single piece of this that you see in there comes from a life form called a crinoid, which we learn a lot more about if you ever take 1404. All right, limestone in particular makes up 10% of all sedimentary rock. most of it being in the ocean, right? That's where all of this is formed. You can get a couple of different types, like I mentioned. We already learned about inorganic limestone. We already talked about travertine, which you get through evaporation processes. Also, by the way, stalactites and stalagmites in caves are made out of that same sort of travertine process. Here I have a chunk of one. Okay, this is all calcite that formed through the same process, a very similar process to travertine. As water evaporates away, it leaves behind very thin layers of calcite, either coming down from the ceiling or building up from the floor as water is dripping from the ceiling in a cave. Carbonate reefs and other fossil limestones. Let me get some fossil limestone here to pass around. There it is. When organisms in the ocean use calcite from the ocean to make their shells, and then those organisms die, and they fall to the bottom of the ocean and they collect there, layer upon layer of dead stuff that has calcite shells or skeletons, you're going to end up with a layer of rock made from those compacted remains. We call that fossil limestone. This is still limestone. It has all the same properties as a micrite I just passed around. It's just that it's made from a bunch of calcite shells instead of just tiny little calcite crystals. Okay? Are you keeping a wary eye on the snake there? Yeah, just making sure it doesn't get too close. Yeah, I got you. All right. You can see it's made out of a lot of shells in there. You guys want to do another logic train real quick? Yeah, sure, go for it. Okay, I love that attitude. If we know that calcite dissolves easier in cold water, would therefore calcite organisms that build their shells out of calcite, would they be living in cold water?
No.
No. As a matter of fact, most organisms that live out in cold water make their shells and exoskeletons and endoskeletons in some cases out of silica. Silica, yeah. So if I am, say, wandering through a cave in New Mexico, let's say, and I go through a layer of limestone in this cave that has silica-rich fossils in it. What does that tell me about my environment?
It used to be cold.
It was cold. Great. Yeah, your face, you're right? Were you messing with me? Were you being sarcastic? No, okay, good. That was a real aha moment. I love aha moments. Okay, if I see that I have a lot of silica-rich fossils in my ocean deposits, I know that that water was cold during that period of time. And then in some layer of rock above it, they all go back to being calcite-based. It got warmer, right? This is just one of the many clues that I can use by understanding how all of this works. One of the many clues that I can follow to interpret things like environment. Paleo environment. Now, before we get a fossil limestone, all those shells have to get fused together first. And believe it or not, there are actually places in the world that we can see this happening right now. I can get a chunk of something off a beach that is in the middle of being between deposited shells and fossil limestone. You will not be happy.
I want to eat it.
Have eaten
When I was
rocks?
younger, I used to eat rocks.
Okay.
Pick them out too, because some of them weren't really crunchy.
Uh-huh.
They wouldn't. Cause I would buy them, they would just hurt. So I'd make sure to pick them out. I'd find the ones that I knew were chalky, from experience, trial and error, and then I would eat those.
Okay, yeah, you know those chocolate rocks? Like what you can get at novelty stores and stuff? When I was like 8 years old, I went to visit my grandpa, and I was being so obnoxious. He got a package of those chocolate rocks. He went out to his backyard, and he had like a rock garden. He just dumped all the chocolate rocks, and he said, look for all the chocolate rocks. You can eat any you find. And I was like, I can eat all of them? He was like, yes, you can eat all of them. I literally spent the entire afternoon out in his backyard going through rock by rock. Nope, that's not one. Oh, I found one. Just like hours. It was genius and also mean, but yes.
I'd say like months, like blue and like.
Some of them are really weird colors, but others actually, yeah. Some of those chocolate rocks look really real. Anyways, Coquina. Okay, so this is a whole bunch of modern day, like these are probably only maybe 100-year-old shell fragments, right? But they have gotten fused together, crushed together, started to melt almost together, this chemical fusing that happens. This is kind of like a medium phase between that loose, those loose shells that you find at the beach and fossil limestone. It's on its way to being fossil limestone. Okay. You can find these a lot in Florida and the Bahamas. You came to say hello, huh? All right. I already passed around the fossil limestone, I think. How many of you have ever been out to the Guadalupe Mountains? They're just a couple hours west of us. Yeah, yeah. You never hiked the Guadalupes or anything like that? I go caving out there all the time. It's really fun. It's cool. Love it. The Guadalupe mountain range is one huge fossilized reef. The entire mountain range. Just a fossilized reef. This whole area used to be covered in water during a time period called the Permian, no less. Hence why we call this the Permian Basin, because all the sediment was deposited during the Permian, filling in that shallow sea that used to be here. Okay? While that shallow sea was here, it was a great environment for stuff to live in, and a massive coral reef grew here. That coral reef eventually, when this area got filled in, got covered in sediment until finally it has been re-exposed at the surface, making what we call the Guadalupe mountain range. So when you go to the Guadalupes, you'll see fossils all over the rock in there. If I ever, like I said, I go caving there all the time. They're not really easy caves to get to, and they're not easy to go in. So I wouldn't like take any of you without first training you for at least like a year. But if I ever were to take any of you in there, the rock's just full of fossils. You can walk along the Guadalupe hiking trails and you find fossils all over. Why? Because it's a reef. The entire thing is fossil limestone. Cool. Now, do you remember in lab 1, there was one mineral that was very similar to calcite, had a lot of the same properties, but you had to scratch a little bit off. You had to powder it a little bit first before you could get it to react with hydrochloric acid. It was called dolomite. Well, as there is a dolomite to the calcite, there is a dolostone to the limestone. Yes. So when I have a limestone and something happens to it, really the only difference between a calcite and a dolomite is one magnesium. There's an optional magnesium that's attached itself to the calcite atomic bond structure. And that's what inhibits that very rapid response to hydrochloric acid. It's very hard for us to tell how this happens. The best we can figure out with some water that is rich in free magnesiums must make its way through the limestone so that those magnesiums can attach themselves to the limestone, right, to the calcite bonds. That's really, and it's hard to test that because testing that would take a long time to push that much water through a bed of limestone and see if it happens. So right now, that's the best we can come up with. That's how it must happen. But either way, we get beds of dolostone. Dolostone have all the same properties of limestone except that fizzy effect. It'll fizz a little bit, but not nearly as wildly as limestone will. Okay? Dolostone. You want me to just, all right, here you go. You got your hands full. Do you remember when I was talking about all of the byproducts that we get of the chemical weathering of feldspar and other silicates? What happens to those free silicons? What happens to the silicon dioxides? The microscopic, the microcrystalline quartz crystal particles. Do you remember where those go? I said that they go through the water until they encounter something, usually like a void, and then they start to form layers inside of that void. And that's how you get agates. Do you remember this now? And geodes. Yeah, that's where those come from. The loose leftover silicon dioxides from chemical weathering of silicate minerals will go on to form these in sedimentary rocks. Yeah. We call this, by the way, chert. You ever heard that term before? Flint, you ever heard of that one? Jasper. All of those are names for the same thing. These buildups, these depositions of microcrystalline quartz that make these structures. Chert, flint, jasper, all of these words for the same stuff. Now, this stuff is very cool. It has the same properties as quartz, meaning that it has conchoidal fracture. Any of y'all ever seen like an old arrowhead? Like a Native American arrowhead? Most of those are made by or made with chert. Because of the unique nature of chert and all quartz to chip along conchoidal fractures, they figured out a way to use bone and wood with the right amount of pressure at the right angle to chip off little pieces of the edge until you can make arrowheads and spearheads and knife handles and axe heads and all of that. Because of this unique geological fact, the way that quartz breaks, they learned how to make weapons out of it. By the way, millions of years ago. Take 1404, we'll talk about exactly how long ago people started making tools out of this. Spoilers, it's about 2.5 million years. Yeah. Okay, we'll talk about that whole thing later on in 1404. But again, this is an aspect of human civilization that owes everything about it to this geological factor. And then evaporates, salt, gypsum. And if you've ever gone on a road trip through Utah? No? If you do, and you go in the summer, take sunglasses. Because there are miles and miles and miles and miles of these flat expanses of dehydrated, just salt and gypsum flatlands. Now, why is it all there? There used to be a massive lake sitting on top of Utah called Lake Bonneville. It's the remains of a massive inland sea that was there that was fed by glacial melt. But over the last thousands of years, that's all evaporated away, leaving only the Great Salt Lake. Okay, the Great Salt Lake is still there in the middle of Utah. It is still evaporating away. It gets smaller every year. Okay, but it left behind all the salt and gypsum that was dissolved in that water. And it is blinding, which is why I advise wearing sunglasses. Okay. Okay. Now let's talk about coal. Geologists are weird. You can always tell a geologist as a kid because they're the ones that really don't mind the thought of getting coal in their stocking, right? My parents would threaten me when I was a kid. You better behave more or you'll get coal in your stocking. You'd be like, bring it. I need coal in my collection, right? And then I realized that wasn't a good threat. And I say, okay, well, we won't give you coal if you're not getting it. They got me there, right? Okay, now coal. Coal is formed through the deposition, not of sediment, which is why this is kind of unique, but the deposition of organic matter, namely plant material. When you have an environment where plant material can fall into a situation where it won't rot away, it won't weather away, right? What causes plant material to, this is a slight tangent, what causes plant material to rot? What causes it to degrade?
Bacteria.
Microorganisms certainly help. What causes everything to degrade? Time and exposure to what?
The air.
Oxygen.
Say that louder.
Oxygen.
Oxygen. Oxygen. Oxygen is breaking everything down. Oxygen is oxidizing. It's causing rust on metal. It's causing plants to degrade. It's causing us to degrade right now. I just killed myself a little bit. Yeah, no, I'm not lying. Do you know why you get older? Do you know why your cells start to fall apart? Do you know why once you reach maturity, human maturity, our bodies start to fall apart? In your DNA are tiny little structures, okay? I'm not going to get too deep into this. Tiny little structures, okay? Tiny little chains of acids that when you bond them with oxygen, they break apart. Yeah,
So we need oxygen to breathe,
we need oxygen to breathe.
but it's also killing.
It's also killing us. Yeah.
Um,
You have stumbled right there upon the quandary of life. Okay? We need oxygen to breathe, but every time that it gets into your system, it kills off these things in your cells. Okay? Yep. Yep. Right? Now our body regenerates these things, but as time goes on and they keep getting destroyed, we can't keep up with the process, and that's why we age. That's why our skin starts to get these nasty, liver spots and stuff like that. That's why our muscles can't keep up. That's why our bones get brittle. All our cells start to fall apart because we can't keep up with the process of the oxidization of your cells at the deepest level. Now, there are lots of people who think it's a fascinating study to try and figure out how to stop that.
How to stop breathing.
You reach the age of 35, you take a medication that stops the oxidization of your DNA. Right? It basically would be like the immortality,
I was about to
right?
say immortality.
Yeah, it would be immortality, at least to that process. You could probably still get shot and die, right?
Yeah.
You could get hit by a car, mauled by a tiger, right? All of these things would still kill you, but age wouldn't, right? So there's lots of people looking into that, which is fascinating. But for now, this is where we are. Now, plants break down under the presence of oxygen, which means that if we can deprive that dead plant of exposure to oxygen, what's going to happen? Yeah, it's not going to break down. We call those environments anoxic. You ever heard that term before? An anoxic environment is one that has been deprived of free oxygens. Classic example of this is a swamp. In the water in a swamp, the water usually doesn't get renewed very much. So if you can remove the oxygen from that water, you will now have water depleted in oxygen, which means that any plant that goes into that water will not degrade, or at least not as quick. How do you deprive it of oxygen? That's where those microorganisms come in. If I have a whole bunch of plants that fall into swamp water, the microorganisms naturally start to degrade them. As they do so, they pull oxygens, bless you, out of the water. You reach a certain point where your water is no longer has enough free oxygens to cause that degradation process. And so more and more plants fall down into that water, piling up on top of each other in this anoxic condition. And eventually they start getting buried deep enough. Something else starts to happen. It starts getting cooked. Exposure to heat and pressure at enough depth causes our buried plants to start getting compacted together. And that's where we get our first form of coal, peat. Are you remembering that joke I told last time? Yeah. This is Pete. Everyone say hi, Pete. I'm just kidding. You didn't have to say that. He's not going to answer you. Okay. He's dead. This is dead plants. But you can look. You can tell that this is little pieces of plants that have been squished together, right?
It looks tasty.
It looks tasty.
Could you actually bite this one?
You can bite any of these, brother.
But like your teeth will actually go through.
Yeah, you would probably take a chunk off this if you tried to eat it.
Okay.
If you bite it, no, but I would laugh. Okay. So this is peat. This is the first phase of coal. Where's my snake at? Oh, you got it. When you're done, would you mind taking it over here? Thank you. All right. That is peat. The next phase is called lignite. If I take that peat and I bury it more and I cook it longer, I start to remove a lot of the stuff, the sulfur, the gases, the volatiles. I can burn peat, by the way.
Don't do that to Pete.
That sounds terrible. Someone's going to clip that. I can burn peat. All right. I can burn that version of coal which we call peat. That's P-E-A-T, by the way. Okay, just to be clear. It's just not very efficient. It wouldn't burn that long. Actually, that reminds me of one of my favorite sayings. If you give a man a match, he'll be warm for a moment. But if you light a man on fire, he'll be warm for the rest of his life.
Yeah, for the rest of his short.
Right. It doesn't matter how long the life is. My point is true, right? Now, yeah, you can burn peat. It won't be very efficient. It'll release a lot of gases. It'll stink like nobody's business. Yeah, stinky peat. Oh boy. Yeah. Did you actually? Okay, good. Don't do that. You need 5. You give him 5.
When y'all give me $5?
Don't do it. Okay.
For money.
This is lignite. This is if I took maybe 2 or 3 feet of peat and then squeezed it and heated it down into this, that's how much of this I would get, okay? It would take a couple feet of peat to make this. Now, you can still see, when it all passes around, you can see there's still like a few plant imprints in there, but nothing in there that I would uniquely say that is a piece of a plant. I can burn this, and it will be far more efficient of a fuel source than peat would be. But this still puts off a lot of sulfur dioxides and stuff like that, things we don't really like emitting today in today's age. But it was lignite, in fact, the coal lignite that fueled the Industrial Revolution. This was the first form of coal that was found in England that fueled that revolution. Okay? Huh? No, I would not recommend biting that one. You like, what are you gonna light it on fire with? It won't light with a match. You gotta maybe with a welding torch. You gotta get it pretty hot. That's the thing with a coal. That's the thing with burning coal. You already have to have some like good heat. Getting a coal fire started is hard, but keeping it going is pretty easy because you just shovel more coal in. It's just a matter of getting it started in the first place. Lighter fluid might, yeah, it might assist with it. Yeah, under the right conditions, and if your lignite is dry enough. Now, the next phase of coal, if I bury it and I cook it a little bit more, I'm going to get the actual true coal, the coal that people think about when I say the word coal. This is called bituminous coal. This is what most of the coal that we produce now is. Okay? This is the most efficient that is generally consumed. I'll tell you why I say it like that in a moment. But this is far cleaner than lignite, but it still puts out some emissions. And so coal mines and coal burning power plants, still a problem, still working on that. There still needs sulfur scrubbers. They still need all of that to remove it from the emissions. And again, same thing. I take, a couple feet of lignite and compress it down, and I end up with some coal. Okay. Now, there is, in fact, one more phase after bituminous coal. If I take bituminous coal and I metamorphose it, which remember is high temperatures and high pressures, we have passed through the realm of sedimentary rock and entered the pressure and temperature regime of metamorphic rock now. If I do that to coal, I end up with anthracite. It's so shiny. It does kind of look like obsidian. Yeah. This is probably the cleanest burning fossil fuel on our planet. This has almost 0 emissions. They've all been cooked out of it. This is the closest we can get to pure energy in solid form. Yeah.
That's pretty cool. You're holding pure energy.
Well, I mean, yeah, you could burn this. It'll burn for a long time. And you can buy anthracite pellets at the store to use in your house and stuff. It's a little expensive. So the question is then, why aren't we using it? Why are we still burning bituminous coal? Why are we using gasoline? Why are we using natural gas? If this is so clean, it's not because we're not that smart. Say that again. The conditions that make this happen at really deep levels, very deep. Most of this is too deep underground to get to. There's only a few places at the surface it comes from. Enough that we can mine it, and you can go to Tractor Supply and you could probably buy a bag of it to heat your home, but not nearly enough to power coal power plants or anything like that. Yeah, nuts indeed. Unfortunate. Oh, a little piece fell off. All right. Now let's talk about that word I mentioned before, diagenesis. Diagenesis is any physical, chemical, or biological change, sometimes biological ones can happen, that occurs after deposition. Any change that occurs after deposition, but before metamorphism. This happens between 150 and 200 degrees Celsius, okay? And starting at a few kilometers of depth. Diagenesis starts at a few kilometers of depth and at 150 degrees Celsius. Part of this process is lithification. Lithification is the process by which sediment becomes sedimentary rock. How? Loose sand in this jar becomes sandstone. Lithification. This involves compaction. So if I have a few feet of sand, I can make 1 foot of sandstone. The general equation here is it takes about 3 feet of sediment to make 1 foot of sedimentary rock. And you ask yourself, how is it possible that you can compact sand that much? There's a lot of air and water usually between the grains of sand. And so bury it under a few kilometers of pressure, and you're going to squeeze all that air and water out until finally you're left with absolutely very, very little space between all those grains. The space between those grains we call porosity, by the way. That'll be more relevant later on. Cementation is what happens after compaction, where water making its way through the compacted sediment deep underground carries with it dissolved stuff like calcite or iron or silica. Yeah, of course. And all of those things can crystallize around our grains of sediment, locking them together. That is called cementation. So on your lab, you're going to notice that one of the questions is, how well cemented is this rock? Well, that's a very simple test. You see if any pieces are falling off.
Yes.
Right. If there are pieces falling off, it's not very well cemented. Oh, right.
And there are pieces that was falling off too.
Okay. So you've learned about how to classify these rocks. We've got your clastic sedimentary rocks. We differentiate those based on grain size, roundness, sorting, shape, yada, yada. Remember, those are characteristics of the grains in them, not the rock themselves. I'm not asking you how round the sedimentary rock is, but how round the grains in it are, right? Then you've got your chemical sedimentary rocks. We tell those apart based upon composition. You've got your silica cherts. You've got your calcite limestones, right? You've got your organic coals, so on and so forth. Any fossils that are present in them can help us differentiate them, okay? So we can use everything that we've learned to draw environmental conclusions. What was the world in that area like when this sediment became a rock? Okay. In combination, by the way, with our igneous knowledge, that gives us great power for determining a lot of the history of our planet, these two things. So here we've got some examples of places where you can find sedimentary rocks. Out here, deep sea fans, material that falls off the continental shelf and goes out into the ocean, right? Lakes, deserts, alluvial fans, swamps, all of these sedimentary rocks we've talked about today are present in these locations, and we can understand the past places where those, let me rephrase that so it makes sense. By understanding the current environments where these sediments are, we can make interpretations about the past environments where the rocks are now found. Yes, of course. Okay, now let's talk about structures for a few minutes. Sedimentary structures are relics of past processes. They tell me about directions of flow. They tell me about energy. They tell me about stuff that used to live there. Some examples: bedding planes. Bedding planes are these natural delineations, these lines that you see here between these layers of rock. I wouldn't call this all one layer of rock. I would call that a layer, and that a layer, and that a layer, and that a layer. And why? Because you can see these natural separations between each layer. Each one of these is called a bed. Something changed. Something in the environment happened that caused this to be different from that. Maybe it's a slight grain size increase. Maybe it was a change in the energy and of flow. Maybe these are more angular than those are, but something is different between this layer and that layer that causes them to be separated like that. Sometimes the separation is just one of color. Sometimes it is actual cracks in the rock like that. Cross bedding is what happens when, in the same way that these flat bedding planes are found, you can see that they are deposited on top of each other in different angles. You see that? Can anyone think of an environment, of a situation in which sediment would be deposited in an angle like that? Why would water do that?
Air, fire.
Say it louder. Why would a river do that? Erosion is transporting it. It's being deposited to end up here, right? Okay, waves. But what are they making? You're at the beach and you walk out and you stick your head in the water and you open your eyes. Either you have goggles or you're okay opening your eyes in salt water, right? And you're looking at the sand underneath of the waves. Do you know what shape they make? Ripples. They make little ripple shapes, almost like little dune shapes. Like this, right? When I have layer upon layer upon layer of sand that are pushed on top of each other at an angle, that gives me cross bedding. This happens with dunes in deserts. This happens with water moving in certain directions, making ripples. But I'll have these different angled beds of sand. Why would I have different angles here? Well, maybe my wind made a dune in this direction, and then my wind changed direction and deposited another one at a slightly different angle on top of it, and then here, and then here, and then here, and then here, all piled on top of each other as time goes on. This is called cross bedding. Graded bedding happens whenever I have, say, an underwater landslide. Okay, like you can see here, it falls off the continental slope and then goes out to the ocean. High energy, lots of different grain sizes, and then once it reaches the bottom here, instantly shut off all the energy, everything falls out, everything is poorly sorted. We get graded bedding, where we have a very rapid drop in energy. And so we have the large and the medium and the small size particles, but they're very intermixed with each other. Okay. And then let's see, we already talked about ripples here. This is what a ripple looks like in rock. They can be preserved in rock. Okay. Those are ripples. That's a structure. Mud cracks also can be preserved in rock. What does that tell me? Whatever body of water I had here evaporated away, right? Leaving behind all the mud cracks. So we can make interpretations based on all these things. And then, of course, fossils. Who doesn't love a good fossil, right? These are all fossils that I have found. These are fossilized tree trunks, some of which I have up here, right here. Let me pass this one around. This one's my favorite. This has been replaced by silica, microcrystalline quartz. It's beautiful. And yes, it does look good enough to eat. Okay? If you think looking at a tree and it's like, oh, that looks good enough to eat is weird. Look at a tree made out of rock and then say that looks good enough to eat. See if people don't think you're weird at all. Okay. Fossilized tree made out of silica now. Every cell replaced by a microscopic crystal of quartz. Found these in Montana, by the way. This is a tyrannosaur rib that I found. Locked in rock, obviously. Can't remove it. There's a funny story to this. It's a funny and tragic story. So I'm out on a dig in Montana, and I find pieces of bone on the surface. These ones here, actually. And I'm putting them together, and I'm trying to figure out what they are. I'm like, wait, this looks like an eyebrow bone structure. So like, okay, this is really cool. This is exciting. Pieces of skull around here somewhere. So I start digging underneath them. I took a picture of these, and then I put my camera over here, And I started like digging and moving things around, and I found an entire Triceratops skull underneath of those. And I exposed a couple feet of it. It's big. I was like, this is so cool. But I spent all my time carefully exposing it. And then the end of the day came. It was the last day of the dig. Our permit expired that day. It was the last day of the dig. There was no way that we were going to get it out of there. So we carefully covered it again and then marked its location so that whoever went there to dig for the next year could remove it. And I never got a picture of it. It completely slipped my mind. I was so excited that I got this picture, and I put my camera over here, and then I covered it all back up, and I picked up my camera and I left, and then on my way home I realized I didn't get a picture of the skull. So I got bits and pieces of the eyebrow, but not the Triceratops skull. It was heartbreaking. That was, let's see, that was 6 years ago. Yeah, someone went back for it. Yeah, they pulled it out. This is a turtle shell that I found only a few feet away from the Triceratops skull. Above it, actually, above it on the hillside, which a few feet above it, a few feet of sediment probably translates to a couple million years of time, right? So this turtle died in whatever environment this was, probably a lake environment, a couple million years more, like most likely after that Triceratops did. We get a lot of non-metallic resources out of sedimentary rocks. This includes oil. Limestone is used a lot. We use it as building material, road material. We crush limestone to make sugars. We crush limestone to remove acids from soils. We use it for a lot of stuff in steel manufacturing. Okay, gypsum. Have you ever dealt with drywall? Any of you ever used drywall for anything like building or anything, where you kicked a hole in your wall? Yeah. Okay. That white dust that comes out of your drywall, that is gypsum powder. We put that in there because it is excellent at absorbing water. Okay, it keeps the inside of your house more protected from the environment, from the elements. We use aggregates like crushed conglomerate for use in making cements and concretes. Right? We have a whole lot of uses for all the things we get out of sedimentary rock. But let's focus on energy for a second here. 84% of all the energy that we produce comes from fossil fuels, which we get from sedimentary rock. This includes coal, petroleum, and natural gas. 37% of it is petroleum, 24% natural gas, 23% coal, only 7% is renewable, and 9% is nuclear. Out of that renewable energy, 53% of that is biomass, okay? 1% is solar, 34% is hydroelectric, geothermal is 5%, and wind is 7%. Out of that 7%, okay? So wind is 7% of the 7% that is our total renewable energy uses. It is literally impossible to run our entire country on renewable energy. When Biden took office, he started this whole thing where he wanted everyone to be fossil fuel independent by 2050. Do you remember that? That was never going to happen. Something that you learn very quick growing up in our world is that politicians don't like math, right? They like saying the things that'll get them elected, but they don't ever bother checking the math to back it up. To power every house in the United States with just wind, we would have to cover an area the size of New Jersey in wind turbines, every square inch of it. And I know New Jersey is a very small town or a very small state, and who would really cry for New Jersey? No, I'm just kidding. But you couldn't do it on New Jersey. They don't have enough wind, right? You would have to spread these things out everywhere, but in area equivalent to that size. That's just every house. If you wanted to power every business and every market, every grocery store, if you want to power every industry, right? Everything that we need, anything that requires electricity in America, and all the vehicles, if you made them all electric, to provide that much energy, you would have to cover an area the size of New Jersey, Delaware, New Hampshire, Rhode Island, Massachusetts. You'd have to cover most of those smaller eastern states in wind turbines. And on top of that, wind is very come and go. Yeah.
Are we really gonna run out of like oil, fossil fuels?
Ooh, that's a good question. Let me finish this thought and I'll come back to that. Okay. It is not possible. It is not efficient. It is not in any way economical to make that many wind turbines. And what happens when the wind stops, right? A quarter of the country loses electricity, right? Because there's no wind in Montana or something, you know? That's not possible. It is not feasible. The question earlier that you just asked was, are we really running out of oil? The answer to that question is no, we are not. Matter of fact, we are nowhere near running out of oil. This oil crisis, it's not a conspiracy. That's not what this means, okay? Has been made because of the amount of regulation that takes place. We still have so much oil underground that we could keep going at our current rate. Today's rate of consumption, we could fuel for about 200 more years. We have a lot. The only problem is
Is that oil here in the US?
it's worldwide. Worldwide oil is what I'm referring to. Most of our oil doesn't come from us, right? We get oil from a lot of other places. A lot of our oil goes to other places. That's the oil market. Okay, it's like its own independent economy, but that's a subject for another time. Okay, we have enough oil to keep going and going and going and going. The problem is the rate at which we can produce oil has been capped, whereas no one is capping how many cars get manufactured. Nobody says you can only produce X number of cars because we can only produce X amount of fuel for them. They say, go nuts on cars, but hey, oil companies, you can only make this much. Yeah, so we are capping production without capping, we're capping supply without capping demand. And environment.
Make it rare, you make more money.
Well, not so much that. It has more to do with preserving the environment. There are good, honest people that honestly, genuinely want to preserve the environment. I'm one of them, right? But then there are other people who say they want to preserve the environment, but really what they do is money cap things. So if you want to produce more, you got to fork it over. Or you can make emissions, but if you want to make more than X amount, fork it over. Right? There's a lot of money to be made in environmental sciences by people who were willing to use the environment for their gain and abuse of the environment for their wealth. So there's a lot of reasons going into why the situation is the way it is, but this oil crisis is entirely the product of man-made decisions. It is not because we are genuinely running out. Okay? Now, emissions are a problem, right? The Earth is warming up and we are contributing to it. I never want to downplay that. But the whole energy crisis is its own separate thing. All right. Let's look at these numbers here. 5,700 kilograms of stone, 178 kilograms of salt, 3,700 kilograms of coal, 3,500 kilograms of petroleum, 3,850 kilograms of natural gas, 9 kilograms of other metals, 249 kilograms of iron. What do all of these numbers of these resources represent? Anthony, this is how many resources you use as an American in a year.
Me?
Yes, you do. You use all that.
Really?
By the way, so do all of you. This is how much of every one of those resources on average, every single one of us needs to sustain our way of life here in America for 1 year. It doesn't just come. Geologists need to find all of that. Yeah. Geologists find every single one of these resources. Yeah.
How do we use the stone and cement?
Stone and cement, the sidewalks you walk on, the foundations for the homes that you live in or the
Like
businesses you visit.
Like we're dividing up all the
Dividing all resources that are used among all Americans that use those resources. Yep, divided equally among all of us, that's how much each one of us requires every year. I know you're thinking to yourself, when did I use 11 kilograms of copper this year? No, but the wiring and the machinery that you use in your phones, in your laptops, in your cars, all of that divided equally among all of us. And by the way, there's like 350 million of us, right? It's a lot of resources. Now, coal distribution in the United States looks like this. Everything that is brown is that lignite. So there's a lot of it up here. This stretches up into Alberta, by the way, okay? Sub-bituminous coal is orange. That's between lignite and bituminous. Bituminous is red. We produce a lot of bituminous coal in America. That's most of what we burn. Anthracite is black. Do you remember why I said we don't use anthracite for everything, even though it burns so clean? It's hard to find. Look, we only have these 3 places that we find anthracite in the United States, and they're tiny by comparison. That's why we don't use it for everything. The rest of it, deep underground. Only in places where that deeply metamorphosed coal has been pushed up to the surface can we mine it. And that's fairly rare. Okay. And then the last thing I want to mention is how oil is formed. I'm sure some of you have wondered this at some point, so let me give you the quick Cliff Notes version. How many of you get that reference, by the way? Do you know what Cliff Notes are? I know you know. You don't know what Cliff Notes are? Cliff Notes is a book series where they take a complicated subject and then make like a 60-page book out of it, so you understand. So it's like Geology Cliff Notes version. Have you ever seen the For Dummies book, like Computer Science for Dummies? That's even older than Cliff Notes. Okay, but it's just a summarized version of a complicated subject. So I'm going to give you the Cliff Notes version of the hydrocarbon process. So we have an ocean environment. This ocean environment full of all sorts of yummy things living in the ocean, right? Sharks, jellyfish, foraminiferans, planktons, all those things, they live, they die, they fall to the bottom of the ocean. They get incorporated, bless you, into the sediment there. That sediment gets buried. As time goes on, more and more of that sediment gets piled on top of it until finally our layer of sediment that is rich in all this organic material gets buried deep enough to start getting cooked, heated, and pressurized. The process of doing so takes those solid hydrocarbon remains and converts them into a liquid. We call that liquid crude oil. So we get crude oil trapped deep underground here under some layer of rock that cannot allow it to move. We call this a trap. It gets trapped somewhere. Now we use our various techniques, seismic interpretation, we drill wells to explore, all this, whatever reason, we find this trapped oil, we poke our straws down there, and we pull it out. Okay, that's where crude oil comes from. What about natural gas? Well, natural gas is what happens when you cook oil too long. It's very hard for us to tell from the surface if what we're looking at down there is actually oil or gas until we drill down to get it. And sometimes we drill down to get it and all we get is gas. And that lets us know, okay, we got here a few million years too late. It got overcooked, left in the oven too long, okay? So that's where crude oil and natural gas comes from. Any questions about today's lecture? Yeah.
Can you also find natural gas in shale?
Yes. Yeah, shale is often the source rock that oil and gas come from. It will form from being cooked in that shale, and it'll migrate out of that shale into more porous rock, usually rock that's under less pressure. So shale is the host rock. Sandstones are usually the production rock, okay, the reservoir rock. Now, those unconventional reservoirs that I talked about before, the unconventional plays, we've kind of found a lot of the easy oil that's in a lot of the sandstones. Now we moved on to unconventional plays, which are, we target the host rock. That shale that the oil was made in still has a lot of oil in it, okay? So we drill down into that, and then we drill sideways into that layer of shale, and then we put a whole lot of water in it, and we pressurize the heck out of it to crack it. Do you know what we call this process? Fracking. You heard that term before? When you frack a rock, you are pressurizing water into it to crack that rock. By cracking that rock, you're making pore space in it that allows the oil in it to flow out. Now you've cracked it with water. So how do you get the oil out? What does oil do with water? It goes up. So you're cracking it with water, and the oil flows up through the water up to the surface where you can pull it out.
So fracking is really not the same.
Drilling is just the process of going down into that layer. Fracking is the process of filling that hole with something that you can crack the rock with. So normally when you're fracking, you'll have your vertical well, and then once you've reached your layer, let's say that this is my layer of rock, I'm going to drill sideways into that layer. And usually it goes out in a whole bunch of different directions. So if I'm looking at this well from the top down, okay, so here's my well hole, I'm drilling sideways wells out like that. And in multiple layers. So that I can pressurize all of that with water, crack that rock up good, and then release the pressure so that the oil can flow out. That's what fracking is.
And is that what is like causing the little earthquakes we're getting?
Induced seismicity is what it's called when we accidentally set off an earthquake ourselves. There's a lot of support to suggest that, yes, this process can encourage that. The pressure from the well, not so much. But what happens if I have, and this is a little bit of a spoiler towards when we talk about earthquakes, but an earthquake happens along what's called a fault plane, which is a crack that has already occurred in the Earth's crust. Along that crack, there's a lot of pressure. What happens, everyone push your hands together like this, okay? Shove your hands together and then try and push your right hand forward. Can't really do it until like you put enough pressure on it that it slips, right? But what would happen if your hands were wet? It would be a lot easier. So by introducing water to a fault surface, we could artificially be accidentally setting off earthquakes early.
So the fault surface that we created.
Well, we don't create fault surfaces. There's already a fault surface somewhere. We just accidentally introduced water to it. That's where a lot of this is probably coming from, this induced seismicity. Now, they do their work, they do the research to try and make sure there are no fault surfaces nearby. Every now and then, one slips through. Or they think that fault isn't collecting enough pressure to make an earthquake. Bless you, but they may have miscalculated. Or perhaps there's a crack, another non-fault crack, some other conduit through which their water escapes this process and makes its way to a fault eventually. There's a lot of research that's gone into this. Okay, any other questions before we move on to lab? Yes?
Isn't it like some type of like wastefulness when doing fracking?
Wastefulness?
Yeah,
I mean, like in the water?
I guess it's like I thought it was like there's only like a little bit of like oil left going on, and it's like a whole issue.
I mean, that depends on the layer. Most of the layers that get fracked are fracked because there's enough oil in there that it is monetarily beneficial to go and get it. When you're losing a lot of water in a fracking well, you know it's going somewhere. And the wise oil company stops because they got to figure out where that water's going. There have been a few bad circumstances. I believe this was a town in Wyoming where one day people turned on their water and it lit on fire. Like there's videos you can find on YouTube. They turn on their sink and they put a match up to it and their water lights on fire because it's full of the gases because they accidentally introduced a fracking well to the water table that all their wells were pulling from. Yeah. So there's some things that you just can't account for. Accidents are going to happen. But when these happen, it's a big part of the reason why people say we shouldn't be fracking because you can't account for all the things that might happen. 90% of the time, nothing happens and we get gasoline for our cars. But it's those few circumstances that give everyone a bad taste in their mouth, for sure. Yeah.
When we do, so we use water, but they also use sand. What's the sand used for? Like,
Yeah, frac sand is used as proppant. So if I pump all that water down there and I crack all that rock, as soon as I release the pressure, what's going to happen to those cracks? They're going to close. So while I still have pressure on that, I'm going to pump a whole bunch of sand down there, really hard quartz sand. that sand is going to get shoved into all those cracks by that pressurized water so that when I release the water pressure so the oil can come out, the cracks are held open by the sand so that the oil can flow. That's what proppant sand is for. Yeah.
Are we going to talk about the carbon cycle?
If I have enough time, I usually do. It's not hugely important. I talk about a lot of it when I talk about this. There is one more slide for those of you that are following on the PowerPoint. There was one more slide about the carbon cycle, but we used a lot of time today, and I want you to have some lab time for lab 3. So I'm going to skip that slide today. I did cover most of it today in class, though. Any other questions before I open up the lab? Asking these questions. These are great questions. Questions make me know that you are interested and concerned, right? Like, I want to know more about this thing. Good. That's why I'm here. All right, well, let's talk about lab 3 real quick then. You got most of what you need to know about lab 3. As usual, your lab PowerPoint is literally just a run through of what we discussed in lecture. It's got a lot of the information that you'll need. Okay, so all the different environments. Okay, so you got your quartz, you've got your calcite, clays, rock fragments. All these are very common ingredients in sedimentary rocks. Okay, so you've got grain sizes, rounding, sorting, cementing quality, all of that. For non-clastic, you've got different types of textures. You've got crystalline textures like your micrites, your skeletal textures like your fossil limestones. Oolitic, let's talk about oolitic limestone for a second here. This is a slightly different variation of the way that we can find calcite. In a shallow, warm sea, you've got those precipitating calcite crystals. They form and then they fall to the bottom, right? But because this is a very shallow sea, the wave action washes them back and forth and back and forth. If I do that long enough, you all fall asleep, okay? But what you end up with is in these warm, shallow seas, you get a whole bunch of little rounded calcite crystals. They were made round by that back and forth motion. So I have a whole bunch of them right here in this bag. It looks like sand, but I promise this is calcite. You drop some acid on this to figure out, because this is what happens when all of that gets compacted together. This is an oolitic limestone. It looks like a sandstone, but guess what? It's as soft as calcite, and it will react to acid. Okay? Best way to tell between oolitic limestone and a quartz sandstone, scratch it, put some acid on it. Okay? That's oolitic limestones. This oolitic, this bag of oolites came from the Bahamas. Oh, careful! Don't put it over a laptop. I think there's a leak in that bag somewhere, because usually I'll find 1 or 2 little oolites dancing around whenever I hold it. So I wouldn't recommend putting it over your laptop. Stratification, that's the bedding planes we talked about. We talked about cross bedding. We talked about graded bedding. We talked about these other structures. They're all just here for your reference. Okay, all the common sedimentary rocks we talked about. You have 12 samples in this lab, just like with lab 2. I asked you about the properties. There's only a few properties, right? If it is clastic, then what are these properties? Or if it is non-clastic, then what are these properties? If you identify it right off the bat as a clastic rock, ignore the if non-clastic section. If you identify it as non-clastic right off the bat, ignore the if clastic section. They are not relevant to each other. It can only be one or the other. Sound good? Great. Then I will end the recording here, and we can begin lab time.